Hi, I'm Martin Saveski, a PhD student at MIT.
And I'm Jean Pouget-Abadie, a PhD student at Harvard.
We're here to tell you more about our paper on detecting network effects in randomized experiments.
Before deploying new features or products, it's a common practice to run randomized experiments, or A/B tests, to estimate the effects of the proposed change. To illustrate how A/B tests work, let's say we want to test a new feed ranking algorithm on the LinkedIn platform. We randomly select a part of the population to get the new version of the algorithm, the treatment, and another randomly selected part to get the current version, the control. We then compare the behavior between the users in the treatment and the control group. This comparison relies on the so-called Sutva assumption, which states that behavior of every user is affected only by their own treatment and not by the treatment of any other user. However, this assumption may not always hold, particularly when testing features on a social platform where users are, by design, connected to each other.
One way to partially mitigate this limitation is by running cluster-based randomized experiments, where we find clusters of densely connected users and we randomly assign each cluster to treatment or control. Now, since users that are connected are more often in the same treatment condition, it is less likely that the treatment effects will spill from the treatment to the control group. Running a cluster-based randomized experiment comes at a cost. Since our unit of analysis is a cluster of users rather than an individual user, the variance of our estimator significantly increases, which in turn reduces our ability to detect network effects. Therefore, knowing whether there are network effects in our experiments can help us decide whether we need to pay the additional cost of running a cluster-based randomized experiment.
In this paper, we propose an experimental design that allows us to detect network effects without making any assumptions about how treatment effects may spill over from the treatment to the control group.
Here is how it works. We first find clusters of densely connected users, and we divide them into two buckets. In the first bucket, we run a completely randomized experiment, and in the second bucket, we run a cluster-based randomized experiment. We then compare the estimates obtained from the two experiments. If there are no network effects, then we expect the two estimates to be very similar. But if the estimates are significantly different, then that is an indication of the presence of network effects.
As part of LinkedIn's internal research efforts, we deployed our experimental design on the LinkedIn experimentation platform, and we ran two experiments testing two different feed ranking algorithms. We ran the first experiment on 20% of all LinkedIn users for 2 weeks, and the second experiment on 36% of all LinkedIn users for 4 weeks. In the first experiment, the treatment effects in the cluster-based experiment were larger, but the difference was not significant. In the second experiment, the difference between the two estimates was much larger, and we found statistically significant network effects.
We hope that our design will help you test for network effects in your experiments.
For more details, check out our paper.
Thanks so much.